أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم Assalamu alaikum to everyone. Today we are going to study about and we will continue the settlement problems. In our previous lecture we discussed and we studied about the immediate settlement. So the settlement which is caused immediately within few days in soils. We will continue that topic. We will determine the modulus of elasticity, that how we can determine in lab and also in the field. And then we will refresh and revisit the concepts which we learned during the Geotech 1 about the vertical stress increases beneath the foundations or different types of foundations. Now, as we all know, that settlement must be estimated with great care for buildings, bridges, towers, power plants, and similar high-cost structures. So these are the structures for which we need to estimate the settlement with great care. Now there are other structures, for example, fills, earth dams, levees, braced sheeting, the sheet pile walls, retaining walls. A great margin of error in the settlements can usually be tolerated. So we can get the approximate values of settlement there, so it should be fine. Now we discussed in our previous lecture that in settlement analysis there are two major problems. One problem is that we need to obtain reliable values of elastic parameters. Elastic parameters is the modulus of elasticity and the Poisson ratio. What are the uncertainties which are causing that error in estimating the elastic parameters? For example, if we are performing test in lab, so the lab values will be less than the modulus of elasticity which we got in the field due to the sample disturbances. And isotropy, which means that if we change the direction of the specimen, for example, if we are measuring the modulus of elasticity or the stress strain behavior in this direction, and if we place and if we apply the stress strain behavior in the horizontal direction, the response will be different, the stress strain response would be different, and it will give us different modulus of elasticity. So that is known as the anisotropy in the soil, and the soils are basically anisotropic in nature. The second problem is obtaining reliable stress profile from the applied loads. So the stress profile from the applied load should also be known or should be calculated. Now there are two problems in that, or sub-problems. First of all, we need to calculate the magnitude or the numerical values of that stress, and then the next point would be how deep we should go for that particular stress profile. So we discussed about different types of footing. We can go for 2B for the square footing, and for 6.5 Z, I would call that, or B, we can go for the strip footing, and 2 into dia in the case of circular footing. Now the next question which comes into our minds would be that how we can determine the modulus of elasticity, or ES. what are the factors affecting ES. Now, in order to answer these questions, first we will go for the factors affecting the modulus of elasticity. For example, we will start with the method of lab test. Now, if we are performing test in our lab, there are various options which are available. For example, the confined test, unconfined test, undrained test, and drained test. If we give you an example about the confined test, we can take example of the odometer test, in which we will get the constrained modulus. In unconfined compression test, we simply place a specimen and we apply an axial load, and we will obtain the stress strain behavior, and from that stress strain behavior at that particular strain level we can calculate the modulus of elasticity using this equation. So the type of test, the type of confinement, and the drainage condition will definitely affect the stress strain behavior of that particular soil. And if those factors are changing the values of modulus of elasticity, so that it could be known as the first factor which will be affecting the modulus of elasticity. Now, in the second case, degree of confinement, and if you remember in the triaxial test, we studied that if a soil specimen is confined, sigma 3 is 50 kilopascal, the stress strain behavior would be different. And if it's 100 kilopascal or 200 kilopascal, the stress strain behavior would be different, and we will be discussing that in our coming slides as well. Over consolidation ratio also affect the modulus of elasticity. So if I say degree of confinement increases, modulus of elasticity increases, and if the OCR increases, modulus of elasticity also increases. How about the soil density? If the density of a soil increases, the modulus of elasticity will also increase. However, if the water content is greater, then the modulus of elasticity will decrease. If we apply higher strain rate, which means that if we are shearing the specimen at a higher strain rate, then the modulus of elasticity will increase. If we are having sample disturbance, if the disturbance of the soil specimen increases, this will decrease the modulus of elasticity. Now, if we perform the triaxial test, and if we plot the stress strain behavior of the deviatoric stress and strain, so we might get a curve like this, a curve like this, or a curve like this one. Now, if you are interested in finding out the initial tangent modulus, so we will simply draw a line, and from that we are getting, I would call that sigma 2, sigma 1 is 0, and here we are getting epsilon 2, and here epsilon 1 would be equal to 0. And if we use this equation, we can find out the modulus of elasticity, ES. Now, we can also find out the secant modulus. And the secant modulus we can find out at the 1/3 of the peak stress. For example, if this is the peak stress, so we can divide, or if we call that as 100 kilopascal, so we will divide in 3 equal increments, 1, 2, and 3. And at this particular point, if we draw a line here, now we can again get the epsilon 2 and epsilon 1 would be equal to 0, and sigma 2 and sigma 1 would be equal to 0. And using this equation, we can find out secant modulus at 1/3 of the peak stress. We can also find out at a particular strain level if it is desired in that particular project. So we can also find out the E50 or E30 at 50% or 30% of the peak stress. Now, what are the lab tests and what are the in situ tests performed to find out the modulus of elasticity? There are many lab tests, but we can use or we can perform the unconfined compression test, which is mostly used in geotechnical engineering to find out the modulus of elasticity. In lab, we can also perform triaxial compression tests, where we can control the drainage conditions and estimate the modulus of elasticity. Now, in situ tests, there are several options which are available, and they are highly recommended. The reason is sample disturbance in lab tests. So standard penetration test, once we get the N value, we can correlate using various correlations to estimate the modulus of elasticity. Cone penetration test, pressure meter test, which will be discussed in today's lecture, and the flat dilatometer test, Iowa stepped blade test, and the plate load test. We can also estimate the modulus of elasticity using the plate load test. Now, if we perform unconfined compression test, and if we apply axial load and with a certain strain rate, we'll come up with a stress strain plot which will look like this. And then if you want to find out the initial tangent modulus or at any particular strain level, we can estimate and calculate the modulus of elasticity from unconfined compression test. You can use that equation to find out the modulus of elasticity. Now, if we want to find out more accurate results, the reason I'm calling it more accurate, because in unconfined compression test, you already know that sigma 3 is equal to 0. Okay, so there is no confinement in unconfined compression test, and we cannot control the drainage there as well. Therefore, we perform unconsolidated undrained test, or we perform consolidated drained test, or we perform consolidated undrained, or we can call that as cannot consolidated undrained test as well, to simulate different field conditions. Now, if we want to perform triaxial test, and the beauty of triaxial test is that we can control the confinement and we can also control the drainage condition. For example, if confinement was provided or the confining pressure was provided here, it's approximately 100 kilopascal, and I would call that as 250 kilopascal approximately, and 470 kilopascal approximately. So as the sigma 3 is increasing, the stress strain behavior is also increasing, or the peak strength is also increasing. So if you want to find out the initial tangent modulus in the small strains, you can see that it's almost the same. A slight increase is occurring, but an obvious increase in the modulus of elasticity can be seen if we are finding at a particular strain level for different confining or increase in the confining pressure. And again, you can use this equation to calculate the modulus of elasticity from triaxial test as well. Now, because of the effects of sample disturbance, it is preferable to determine E, or the shear modulus, which is G, from the results of in situ tests. And for that purpose, standard penetration tests or cone penetration tests are performed, and others which will be discussed in today's lecture. Now, what we get from the standard penetration test, we get the standard penetration test N value there, which is N55 in these correlations, and we can estimate for various types of soils the modulus of elasticity for that particular soil if we have the SPT N value. We can also estimate the modulus of elasticity if we are given with the cone tip resistance, which is QC, and sleeve friction. But if you have the tip resistance from the cone penetration test, we can also use any of these correlations depending upon the type of the soil which we classify during the grain size distribution. If we classify the soil, there are different modulus of elasticity values are given that are based upon the soil, or that particular soil. For example, if it's sand and gravel, and if it's loose or dense, so you can approximately take a value there. And particularly these are useful when you are doing numerical analysis using fluxes GeoStudio. These are the softwares, Slide, and many others in geotechnical engineering. The pressure meter test is performed to estimate the modulus of elasticity. In-depth understanding is not desired at undergraduate level. It is taught in situ tests and postgraduate studies, but a general behavior that how we estimate the modulus of elasticity in the field is shown in this slide. Now we are given with this device. There are two guard cells and one measuring cell, and we need to lower that those guard cells and measuring cells in a borehole. And this measuring cell, using the water pressure, will try to expand into the soil, and that soil is under test condition, this one as well. So it will try to expand, and based upon the volume change which is occurring due to the pressure which is exerted due by the water in this measuring cell, will give us a curve like this. And from this pressure or the stress volume curve, the stress strain curve, we can estimate the modulus of elasticity from the change in the pressures and the change in the volume. Zoom in view of this particular location in the borehole is given here. There is another test which is the flat dilatometer test. So usually it's flat, and you can use the CPT, cone penetration rig here. So you will penetrate into the soil without having a borehole there, and it's a flat plate, but the zoom in view shows that there is a membrane, circular membrane, and if you are looking from this side, so it will look like a thin plate. Now a high pressure nitrogen gas is used to inflate this membrane. Now if the high pressure nitrogen gas is inserted here, now this membrane will inflate or expand, and it will exert some pressure onto this test soil which is surrounding this membrane. And from the stress strain behavior can be also plotted to estimate the modulus of elasticity. Please confirm that you can hear me and the screen is visible.
Yes, sir.
Okay, thank you. Now here in this slide, it is shown that at a particular depth, 1.5 meter and 4.5 meter, we collected two soil specimens, and how we estimate the confining pressure in the triaxial test. So if we assume that the friction angle for that cohesionless soil is 35 degree, the lateral pressure coefficient we can calculate using this equation. It's 0.426, and the overburden we can easily estimate using this equation at that particular depth of 1.5 meter, and sigma naught at the 0.2 would be 4.5 into gamma. So if we estimate the sigma 1 and sigma 2, we can find out the sigma 3, which is the lateral or the confining pressure, using K0 into sigma 1, and approximately it would be 15, but we can test that at 20 kilopascal for the factor of safety. Now we can also take 40 kilopascal for the soil specimen taken from the depth of number 2 point, which is Z equal to 4.5 meter. Once we collect that, we will find out the delta Q, which would be the deviator stress at failure, and we can estimate the modulus of elasticity, or we can also calculate the secant modulus. For example, we prepared the specimen and we confined it to 20 kilopascal. So this would be the stress strain behavior. And we performed another test from number 2 location, and we got the stress strain behavior something like this. Now, if you are interested at that particular strain level, for this depth 1.5 meter, so you can see that the modulus of elasticity would be smaller for the number 1 location, which is at shallower depth, and for deep soil, because the soil will be dense, it will be over consolidated, overburden pressures are higher at greater depth. Therefore, the modulus of elasticity for soil specimen which is taken at greater depth would be greater compared to the shallower depth. So just giving you the confirmation that what we studied in factors affecting the modulus of elasticity. Once you know the modulus of elasticity E, then you can find out the shear modulus, which is also used in the foundation design. Now, Poisson ratio, you can assume, for example, if we are having an undrained clays, is equal to 0.50, and for drained condition, it's usually 0.33. We can also estimate the Poisson ratio if we know the lateral strains and the volumetric strains. Now, how we find out the lateral strains? So usually in advanced geotechnical testing, radial strain transducers are used to find out the lateral strains. And if you remember back pressure, or we will call that back volume pumps, are used to find out the volumetric strains in triaxial testing. Various ranges of Poisson's ratio for a particular type of soil, like clay, if it's in saturated condition, the Poisson ratio would be in the range of this one. And if we are having a sandy clay, the Poisson ratio would be in this range for sand, gravel, and sand. So it would be in this range. So these values are particularly important when we want to perform the numerical analysis and we don't want to spend too much money on the lab and field tests. So that was all about the modulus of elasticity factors and the determination methods. Now we will refresh your concept on the variation of the vertical stress or the stress increase if a load is applied at this particular point. If there was no load, then we already know that we will be having overburden pressure, which will increase with the increase in the depth of the soil. But when the load is applied, and if you are asked to find out the stress increase, and I would call that as delta sigma Z or delta sigma V, and here is the delta sigma X. Okay, so in our previous lectures or in Geotech 2, our focus was on the sigma naught or the overburden pressures. Now in this lecture, we want to know that what would be the stress increase at a particular distance, and that distance is R. Okay, for a point load, that is important. Now as we go deeper, so at this particular point, the stress increase due to the point load would be higher, and as we are going downwards or beneath the foundation, this stress increase will become less. Okay, and then we will reach to a point where we will come up with 0.1 or 10% of the contact pressure. Please kindly note down this equation. For a point load, the stress increase delta sigma, and this is particularly for the point load, 3q divided by 2 pi z square, and this term in which q is the load which is applied and that point load, z is the depth of interest, r is this distance away from the center line, and again z is the depth of the interest. Q is known, z is known. We can replace this term by the influence factor, and I will explain that how we will find out this influence factor using a graph. So we can estimate the stress increase which is caused at this particular point when this point load is applied. Now, if we are moving away from the center line, so this stress increase will decrease in such a manner. Okay. Now, what if we are given with a line load, and in case of line load, you can use this equation to find out the stress increase at a particular distance x from the central line. So this would be the delta sigma z, and here it would be delta sigma x. Now, if we are given with a strip area and carrying a uniform pressure, this is the strip area, and if you are asked to find out the stress increase at this particular point and at this particular depth, see, now you will start from here, and from the right corner of the strip footing, this angle could be alpha, which is being used in this equation. Now, if you draw a vertical line, and the line which is coming from the right corner of the strip footing, that B which is being used in here, Z is there, and also what else? Alpha, sine alpha, cos alpha, Q, and Q is the pressure intensity which is exerted on top of that strip footing. Now, if you remember, we talk about this depth Z, that what would be the depth Z. For example, if I draw something like this, the pressure bulbs, I'm going a bit far on the right side. So we will end up with a point where we will be having 10% of the pressure which is exerted onto the strip footing. We need to find out the depth Z. If we use the previous equation for the strip footing, and if we insert sigma Z, or the delta sigma Z, which is equal to 10% of the Q, so we will come up with the depth at which we will be having 10% of Q. In other words, we can say that this isobar will give us 0.1 Q. Why it is important? It is important to know at least the soil information at this particular depth, like what type of soil is there in this particular depth. Now, a strip footing is given with 2 meter wide. Uniform pressure Q is given on the surface of a deposit of sand. The water table is at the surface. The saturated unit weight of the sand is 20. So gamma saturated is given. K naught is given. We need to determine the vertical delta sigma Z and the horizontal stresses at a point Z. This would be delta sigma X, and Z is equal to 3 meter below the center of the footing before and after the application of the pressure. Now, if there is no pressure, we can simply find out sigma prime Z by gamma into Z, and Z is 3 meter, and gamma prime would be equal to 10.2, subtracting the unit weight of water. If you simply multiply K naught with this value of sigma prime Z, we'll come up with the sigma prime X. Now, in order to find out delta sigma Z and delta sigma X, we can use these equations to calculate delta sigma Z and delta sigma X. then if we want to find out the sigma prime c, so it would be something I would call that sigma naught plus delta sigma, and again this would be sigma naught plus delta sigma. Okay, and that delta sigma we calculate it from here. Why we need to find out those delta sigma are the stress increases. So you already know that if we are having a soil initially without a foundation load on top of this soil, so this we can call that as sigma naught prime, and this load, which is the stress increase due to this particular load is occurring, that's how we can calculate using different equations for different types of foundations. For example, if we are given with a circular area having a uniform pressure is exerted, then we will use this equation to find out the delta sigma c beneath the circular area. Please kindly note down this equation as well, it is very important. And if you can see here that this term has been replaced by the term IC, which is the influence factor, and we can find out the influence factor using this figure. This is the IC from d by z, and d is the diameter of the circular footing, and z is the depth under the center of circular area at which we want to find out the vertical stress or the stress increase. Now, there are two methods to find out delta sigma, and that delta sigma we can find out using the Bosenisk method, and the second method is Slotuan method. First we will discuss the Bosenisk method, and then we will discuss the Slotuan method. Please kindly note down this equation. Delta sigma we can find out from the Q naught, and Q naught is the contact pressure. M is the number of contributing corners to delta sigma. For example, M is equal to 1 if we are finding under the corner, and M is equal to 4 if we are finding at the center. I sigma is the influence factor, which I will explain that how we can find the I sigma from this particular graph. Now we can replace that as MC or NZ. M is here and N is here. M we can find out, for example, P prime divided by C, and N is equal to L prime divided by C. If you interchange M and N, so the value of I sigma won't change. So you don't need to worry about changing M or N. If you call, for example, M is equal to L prime divided by Z, or N is equal to B prime divided by Z, so you are ultimately getting this value based upon the M, and these curves shows the N values. Sample questions are given that if you want to find out the vertical stress at a depth of 3 meter below a point of the central line 1.5 meter outside a long edge of the foundation. For example, this is the point, and here is the rectangular footing. I would say stress increase or delta sigma for this rectangular footing would be equal to the stress increase which we find out for this. I would call that as A is equal to B minus C. So if I call that as C, so we need to subtract the stress increase which we got from this portion. So it's kind of a superposition. And if we subtract the stress increase which we find out from this rectangular section or this part and from the B which we got from this one, in this case we can see that we will find out the M and we will find out the N, and once we find out the M and N using, let's suppose, B prime divided by C and L prime divided by C, and then we will find out the I sigma, and once we get the I sigma we can use the Boson's coefficient here to find out the delta sigma. And if you want to find out the delta sigma, for example 1, delta sigma 2 and delta sigma 3, which is obtained from the 1.5 meter which is away from the rectangular footing. Now talking about the slope 2-1 method, in slope 2-1 method it is proposed that if a load is applied onto a footing here, this will be P, and this portion would be C by 2, and this portion would be equal to C by 2 as well. Now for the rectangular footing, delta sigma would be equal to Q divided by B plus C, and that Q is the load which is applied here, B is the width of the footing, and C is the depth of the interest at which we want to find out the stress increase. If we are given with the square base, then delta sigma would be equal to Q by B plus Z square. Please kindly note down these equations as well, because we are going to use in solving examples and problems. Now here is a very important concept which has been discussed. For example, if load Q or P is applied, and if it is requested to find out the stress increase, so we already know that the stress increase would be greater near to the foundation at a shallower depth, and then it will decrease. So this will give us an area which is known as area 1, and you can simply integrate the area from Z1 to Z2 delta sigma dz. Now we need to find out the delta sigma average, because one value of delta sigma is used in finding the settlement of the foundation. And if we find out the area 1, and that we can do using the Simpson's rule, which I will explain in coming slides. But for the time being, you can note down this equation if you want to find out the delta sigma. If you know the Q, B, and Z1. Please also note down that Z1 is taken from the base of the foundation, and Z2 is also taken from the base of the foundation till the bottom of the second layer. Now in this problem, we need to find out the average stress increase in 10 feet thick clay layer using slope 2-1 method. So a load is applied at a depth of 10 feet. The dimensions are given. Here I would say it's 3.5 feet. .5 feet. And we need to find out the stress increase delta sigma for this clay layer of 10 feet. So if we use this equation, Q divided by B plus Z1 and B plus Z2. So what would be the value of Z1? So you can take the value of Z1 from this base of the footing, which is, I guess, 6 feet, and then you can take Z2, which would be 16 feet. Q is also given. Else we know. We want to know about the B, which is 8 feet. So if you plug in those values, you will come up with the delta sigma value 1.11 kips per square feet. It's pretty much simple. Now we need to find out the average stress increase in 10 feet thick clay layer using Bosnisk equation. Now you need to find out the stress increase using the Bosnisk equation. Same problem, but now you need to use another method to find out the delta sigma. Please confirm that you can hear me and the voice is clear.
Yes, sir.
Okay, thank you. Now here you need to remember a very important point, that for example at this particular depth, as we discussed earlier on, that the stress increase would be greater at shallower depths. Now if we need to find out the area of this portion, and why we need to find out the area of this portion, because we need to find out the delta sigma average, which we need to find out the settlement. So what we can simply do, we can construct a table here. Q naught is the load per unit area and 375 kips is applied. So this would be the Q naught. Now we need to construct a table first, like the serial number 1, 2, 3, and 4, and 5. We will divide this layer, this 10 feet layer, in equal increments of 2.5 feet. Okay, so we will divide this layer. This would be 2.84. I will explain that how we got there. Delta sigma 1, and this would be delta sigma 2, delta sigma 3, delta sigma 4, and this value 0.63 would be delta sigma 5. Why I wrote these values here? Because we are going to use the Simpson's rule, which we study in numerical analysis in earlier years of civil engineering. So first we will find out at 6 feet, and then we will add 2.5. It will be 8.5, and then we will again add 2.5 feet. It will be 11 feet, and then we will add 2.5. It will be 13.5 feet, and then we will again add 2.5 feet at the bottom of this 10 feet clay layer. So it's like 10 feet clay layer. Then we will find out M, which should be B prime divided by C. Then we will find out the N, which will be L prime divided by C. And once we get those two M and N values there, we will come up to this figure. Now we got 0.67, 0.1, 2, 3, 4, 5, 6, and 7. And here it's somewhere here, I would say. Okay, 0 point, let's see. So almost close to 0.12. Okay, so you can choose the value of 0.12 I sigma. So we need a correction here. It's 0.12, and it's a rectangular footing, and just beneath the foundation, we can assume m is equal to 4. Yeah, m is equal to 4 here. Q naught is given, and once you find out the I sigma from that figure, you can easily find out the delta sigma. So this would be 1, delta sigma 2, delta sigma 3, delta sigma 4, delta sigma 5. Now we need to find out the delta sigma average. How we are going to find out the delta sigma average? So you need to use the Simpson rule to find the average area. And please kindly note down this equation, that how you can find out the area to find out the average area, and then you can calculate the delta sigma. So if you see here, it looks very complicated, but don't worry. I will explain. Delta H is the interval of 2.5 feet. So you can insert that 2.5 feet here. Delta sigma 1 is this delta sigma 1 2.84. That's okay. Now delta sigma, this is delta sigma n, which means that how many values we have. So the last value is delta sigma 5, which is 0.63. So you can include that here, divide by 2 plus 1.81 delta sigma 2, which is here, delta sigma 3 then, which is here, and delta sigma 4, which is here, delta sigma 4. So you'll come up with the area which we got in kips per feet, and if we simply multiply that 10 feet layer, it will give you, sorry, if we divide that area by 10 feet, so we will come up with the delta sigma, which is the stress increase, which we want. Okay, now please repeat this same problem. It's a home assignment, and in a home assignment, it means that it's just for your practice. Try it for the circular footing. So we did for the rectangular. Now you need to repeat the same problem using the circular footing, and how they came up with the 9 feet. So they came up with the area which will give us the same stress at this particular point, at this contact stress, which is equal to 5.8 something, yeah, here. So in order to get this Q naught contact stress equal to 5.859, 9 feet, you can easily find out the area, and then you can find out the radius from and the diameter of this circular footing. So in order to get this value, 9 feet is extracted in this problem. Now you need to find out the stress increase due to the similar loading condition and similar soil condition. So this is 16 feet, okay, and this is 10 feet. Unit weights are given, water table information is given, rest of the information is same. I will explain a little bit here. If you remember, for a circular footing, you're given with the an equation, yeah, circular area having a uniform pressure. So delta sigma z we can find out from the contact stress, and if we know the radius r, and if we have the depth of the interest, or even if we use this figure d by z, so from that particular d by z we can easily calculate the IC value as well. But we can calculate by finding each and every term, and then we multiply with the Q to find out delta sigma z, the stress increase due to that uniform load which is applied onto a circular footing. So please kindly repeat that problem. Questions are given, and solution is also given. You can see here the depth is given 6 feet and 8.5, so the interval is 2.5 feet. So you will find out first r by z, and then you will find out 1 plus r by z square, and then 1 divided by 1 plus rz square, and whole of 3 by 2. And then in order to find out the IC, you will subtract this column number 4 from 1. And once you got that delta sigma z into Q I sigma or IC, and that is equal to 1.415. So what was the delta sigma? So a slight change you can see that is 1.404 KSF, and here it's 1.415 KSF. That is due to the shape of the footing. Okay, thank you very much for listening very patiently. Now we will move towards question and answer session.